of the subject Engineering Mathematics, Chapter 1 Linear Algebra. Now in this session we discuss classroom workbook questions on the concepts Cayley-Hamilton theorem and spectral theorem. Just go through your handout. Let us start classroom workbook from question number 64. Just let us go through handout. Start from question number 64. If A equal to a 4 by 4 matrix is given 1 0 0 1 0 minus 1 0 minus 1 0 0 I 0 0 0 minus I, then a power 4 equal to blank. This is the question. Now when you look at this equation, the size of this matrix is 4 by 4. Now interestingly they asked a power 4. So when you try to find its characteristic equation, the highest power of lambda is 4 and replace lambda by a, you will get a power 4. Simple. The size of this matrix is 4. So when you define its characteristic equation, it is a 4th degree polynomial. What does it mean? The highest power of lambda is 4. Now replace lambda by a, you get a power 4. Let us see. Here what are my diagonal elements? 1 minus 1, I minus I. All elements below diagonal are 0. Therefore my eigenvalues are 1 minus 1, I minus I. Therefore its characteristic equation is lambda minus 1 into lambda plus 1 into lambda minus I into lambda plus I equal to 0. Now simplify this. This is lambda square minus 1 into lambda square plus 1 equal to 0. So here I is a complex number whose square is minus 1. This is the standard symbol I or j. Now this implies lambda power 4 minus 1 is 0. Therefore we got lambda power 4 equal to 1. Now apply Cayley-Hamilton theorem at this moment. Cayley-Hamilton theorem. CH means Cayley-Hamilton. Then replace lambda by a power 4 and replace the last constant by I. Therefore a power 4 equal to I. Work out this. Now let us move to question number 65. Given that a equal to minus 5 minus 3 2 0, I equal to 1 0 0 1 1 0 0 1. Then they were asking the expression for a cube in terms of a. So A is 2 by 2 matrix, I is 2 by 2 identity matrix. They asked a cube. When you look at options, everything is in terms of A. So that means we need to find positive powers of A. This can be done in two different ways. First of all, let us try this by using Cayley-Hamilton theorem. The basic advantage of Cayley-Hamilton theorem is you can find the positive powers of a matrix A in terms of A itself. So for this, let us find its characteristic equation. Now let us see, in this case, when you add columns, add first column, you will get minus 3. Add second column, you get minus 3. So minus 3 is one of its eigenvalue. But trace is minus 5, already minus 3 is covered, so second eigenvalue is minus 2. So the characteristic equation is lambda plus 3 into lambda plus 2 equal to 0. This implies lambda square plus 2 lambda plus 5 lambda, 3 lambda, this is 5 lambda plus 6 equal to 0. Now apply Cayley-Hamilton theorem, that is replace lambda by a, we get a square plus 5a plus the last constant is replaced by 6 into I. This is number 0, this is matrix O. Therefore a square equal to minus 5a minus 6i. but we want a cube. So multiply this with a on both sides. So a cube equal to minus 5a square minus 6a. This is a minus 5 into a square is replaced by this minus 5a minus 6i minus 6a. So this is 25a minus 6a, 19a plus 30i. Therefore, the value of a cube is 19a plus 30i. So this is by using Cayley-Hamilton theorem. So according to options, option B is right answer. Note this. Now let us solve this question by spectral theorem. What are the eigenvalues of the matrix A? Minus 2, minus 3. Now we need a cube. So the eigenvalues of a cube are minus 2 whole cube, comma minus 3 whole cube. Now I was solving this question. I am solving this question by using spectral theorem. Previous one is by using Cayley-Hamilton theorem. So therefore the eigenvalues of a cube are minus 8, minus 27. Now let us come to option A. The first option is 15a plus 12i. Now let us find the eigenvalues of first option. Replace a by minus 2, 15 into minus 2, just verification of options, plus 12 into eigenvalues of 1 are I are 1 only. So therefore this is a minus 30 plus 12, this is minus 18. But minus 18 is not at all an eigenvalue of a cube. Just you find the eigenvalues of a. We want a cube. So let us try to find eigenvalues of a cube and then verify options by using spectral theorem. So the eigenvalues of a cube are minus 2 whole cube, minus 3 whole cube. They are minus 8 and minus 27. Now for the first option, 15a plus 12i, one of the eigenvalue is minus 18. But minus 18 is not an eigenvalue of a cube. So eliminate option 1. Now come to option 2. This is 19a plus 30i. Now replace a by minus 2. So this is 19 into minus 2 plus 30 into 1. Therefore this is minus 8. Minus 8 is one of the eigenvalue of a cube. So one eigenvalue is matched. So let us try to find second eigenvalue. Replace a by second eigenvalue. So 19 into minus 3 plus 30 into 1. So this is minus 27. So minus 27 is matching with eigenvalue of a cube. Therefore, it matches with all eigenvalues of a cube. Even when you go through option C and option D, at least one eigenvalue does not match. Therefore, for the second option, eigenvalues are minus a and minus 27. This is by spectral theorem. And for the a cube, the eigenvalues are minus 8, minus 27. Therefore, eigenvalues of a cube are same as eigenvalues of second option only. Therefore, B is right answer. This is by using spectral theorem, just by verification. Note down this also. See, the advantage of spectral theorem is when the large powers of a are given, instead of giving a cube, if they ask you a power 16, then instead of doing this question by Cayley-Hamilton theorem, if you do this by spectral theorem, you get the answer very easily. So for larger powers, spectral theorem is so flexible. For smaller powers, it doesn't matter whether you apply Cayley-Hamilton theorem or spectral theorem. Is this clear? Now let us move to question number 66. Question number 66. It is given that A is a 3 by 3 matrix with eigenvalues 1, -1, 0. Then they were asking det of I plus a power 100. Det of I plus a power 100. So when you simplify this, you get a 3 by 3 matrix. So it has certainly 3 eigenvalues. But eigenvalues of A are this. So let us try to find eigenvalues of this expression. So let E of A equal to I plus a power 100. Now let us try to apply spectral theorem. So what is the first eigenvalue of E of A? E of 1. So E of 1 equal to replace I by 1 because all eigenvalues of I are 1 only. So 1 plus 1 power 100, this is 2. Now replace A by second eigenvalue, E of -1. This is 1 plus -1 whole power 100. This is again 2. Now replace A by 0 because third eigenvalue is 0. This is 1 plus 0 power 100. This is 1. Therefore, the eigenvalues of this combination matrix are 2, 2, 1. Therefore, the det of this matrix is product of these two eigenvalues. It is 2 into 2 into 1. So, the result is 4. Just by using spectral theorem. Now let's move to question number 67. So 68. Sorry, we moved to question number 67 instead of 66. This was actually question number 67. This was actually question number 67. Now let us solve question number 66. Question number 66. Suppose M is a 3 by 3 matrix with eigenvalues 1, 2, 3. And it is given that M inverse equal to M square by alpha minus M plus 11 by alpha into I3 for some scalar alpha not equal to 0. Then what is value of alpha? This is the given question. So M is a 3 by 3 matrix with eigenvalues 1, 2, 3 and M inverse is given in terms of M. So when M inverse is given in terms of M, this is a simple application of Cayley-Hamilton theorem. So for that what you need to do? You need to find characteristic equation because all eigenvalues are given 1, 2, 3. So its characteristic equation is lambda minus 1 into lambda minus 2 into lambda minus 3 equal to 0. Simplify that expression, you will get an equation in terms of lambda with degree 3 and apply Cayley-Hamilton theorem by replacing lambda by M and then multiply with M inverse. You will get some expression and compare that expression with given M inverse, you will get the value of alpha. Is this point clear? See here M inverse is given in terms of M. That means this is a simple application of Cayley-Hamilton theorem. Now how to handle this by using Cayley-Hamilton theorem? Just using these three eigenvalues, try to find its characteristic equation. What it is? Lambda minus 1 into lambda minus 2 into lambda minus 3 equal to 0. You get a third degree expression. Replace lambda by M. So you will get M cube, something like that. And then multiply that expression with M inverse. You will get some expression for M inverse in terms of M. Compare your expression for M inverse with this. You will get alpha value. So it takes some 6 to 7 steps. But instead of doing that by use Cayley-Hamilton theorem, we can solve this by spectral theorem very easily. Let us see. Now these three are eigenvalues of M. You use any eigenvalue, replace M by any one of eigenvalue. Suppose I am replacing M by 1. So 1 inverse equal to 1 square by alpha minus 1 plus 11 by alpha into eigenvalues of I3 are 1. This implies 1 equal to 12 by alpha minus 1. This implies 2 equal to 12 by alpha. This implies alpha equal to 6. Even you can replace m by 2 also. Let us see. Replace m by 2 any eigenvalue. So 2 inverse equal to 2 square by alpha minus 2 plus 11 by alpha into eigenvalues of identity matrix are 1 only. So this implies 1 by 2 equal to 15 by alpha minus 2. This implies 1 by 2 plus 2. So this is 5 by 2 equal to 15 by alpha. Now therefore you will get alpha equal to 6. This is by spectral theorem. Note this. Now let us move to question number 68. So question number 68. Suppose if p equal to 1 1, then they were asking p power 8 minus 2 into p power 7 plus 2 into p power 6 minus 4 into p power 5 plus 3p power 4 minus 6p cube plus 2p square. 2p square equal to some options are given. Let me write out the options. First option is p, second option 2p, third option 3p, fourth option is 4p. Now again you try to apply spectral theorem by finding eigenvalues of this and this, and then you can apply verification. Let us see. Here this is a 2 by 2 matrix. What are its eigenvalues? Its eigenvalues are 0, 2. 1 plus 1, 2, 1 plus 1, 2. So 2. Already trace is 2, 2 is covered, so it is 0. Or simple words, its a det is 0. So at least one eigenvalue will be 0. Therefore the eigenvalues of this matrix are 0 and 2. Now let us try to find eigenvalues of this polynomial expression. We call this as E of p. Therefore its eigenvalues are E of 0. One of its eigenvalues are E of 0. Replace p by 0, you will get 0. Second eigenvalue is E of 2. Replace p by 2. So 2 power 8 minus 2 into 2 power 7 plus 2 into 2 power 6 minus 4 into 2 power 5 plus 3 into 2 power 4 minus 6 into 2 cube plus 2 into 2 square. Now this term and this term will be cancelled. This and this will be cancelled. This and this will be cancelled. So this is 8. Therefore the eigenvalues of this E of p are, the eigenvalues of E of p are 0, 8. Now let us find the eigenvalues of options. For the first combination the eigenvalues are 0, 2. For the second option 2 into 0, 2 into 2, 4. For this 3 into 0, 3 into 2, 6. Only this option has eigenvalues 0, 8. So the last option has eigenvalues 0, 8 which are matching with eigenvalues of this complicated expression. Therefore this is nothing but 4p. Therefore option D is right. Note this. Now let us discuss question number 69. Let A equal to the matrix 1 0 minus 1 minus 1 2 0 0 0 minus 2 and B equal to A cube minus A square minus 4a plus 5i, where I is 3 by 3 identity matrix. That is very clear. So they were asking det of B. We need to find det of this matrix. So basically this is nothing but an expression in terms of A. So first let us try to find eigenvalues of A. Once you get 3 eigenvalues of A, then you try to find eigenvalues of this B and multiply those eigenvalues, that becomes det of this matrix. I repeat once again. A is given like this, 3 by 3 matrix. They were asking determinant of this matrix B, where B equal to this, a cube minus a square minus 4a plus 5i. So this is an expression in terms of A. First let us try to find eigenvalues of A, either by characteristic equation or by uniform sum property or by singular matrix, whichever is applicable. Try to find out eigenvalues of this matrix by that process. So get the eigenvalues of this matrix. You get 3 eigenvalues. Replace those 3 in this, you will get 3 eigenvalues. And they become eigenvalues of this 3 by 3 matrix B. And multiply those eigenvalues, that is nothing but det of this matrix. Now let us see. So is there any uniform sum regarding rows or columns? I don't think so. Here when you add these 3, you will get 0. But in this case 2, no use. Row wise 0, it is 1, no use at all. Now let us try to find its eigenvalues by using its characteristic equation, because in the last row we have 2 zeros. So let us try to find its eigenvalues by characteristic equation. Det of a minus lambda I equal to 0. Now this implies subtract lambda from diagonal elements. So this is 1 minus lambda 0 minus 1 minus 1 2 minus lambda 0 0 0 2 minus lambda equal to 0. Now this is, in the last row we have 2 zeros expanded with respect to last row. So 2 minus lambda into det of this block. So det of 1 minus lambda 0 minus 1 2 minus lambda equal to 0. Now this implies 2 minus lambda into, now this is a lower triangular matrix. Diagonal elements are 1 minus lambda, 2 minus lambda, above diagonal element is 0. It is a lower triangular. So that is product of diagonal elements, 1 minus lambda into 2 minus lambda equal to 0. Therefore my eigenvalues are 2, 1, 2. So therefore one eigenvalue is repeated twice. So these 3 are eigenvalues of the matrix A. Now let us find the eigenvalues of B. One of the eigenvalue of B is replace A by 1. So this is 1 minus 1 minus 4 plus 5. 5 plus 1 is 6. 6 minus 5. This is 1. So second eigenvalue is replace A by 2. I am applying spectral theorem. 2 cube minus 2 square minus 4 into 2 plus 5 into 1. Now this is 8 minus 4 minus 8 plus 5. Therefore this is nothing but 8 will cancel. Now this is 1. So replace another eigenvalue is 2. Therefore another eigenvalue is 1. Therefore the eigenvalues of B are 1 1 1. The eigenvalues of B are 1 1 1. Therefore det B equal to multiply all these 1 into 1 into 1. So the result is 1. Note this. Now let us discuss question number 70. So let M be a 2 by 2 matrix with eigenvalues 1 comma 2. Then they were asking M inverse in terms of M. So you can handle this question by using spectral theorem or by Cayley-Hamilton theorem. Since it is a 2 by 2 matrix, you can handle very easily with Cayley-Hamilton theorem. Since these two are eigenvalues of M, my characteristic equation is this. Lambda minus 1 into lambda minus 2 equal to 0. This implies lambda square minus 3 lambda plus 2 equal to 0. So by Cayley-Hamilton theorem, this is m square minus 3m plus 2I equal to null matrix. Now multiply this with m inverse both sides. So m inverse into m square minus 3m plus 2I equal to m inverse into null matrix, null matrix. This implies m minus 3I plus 2 into m inverse equal to O. Therefore, 2 into m inverse equal to 3I minus m. Therefore, m inverse equal to 3I minus m divided by 2. So, this is the value of m inverse. Option number C is right. Option C is right. Now, let us discuss question number 71. This will be the last question on the models Cayley-Hamilton theorem or spectral theorem. Given that A equal to 3113, question number 71, last question in this model, A equal to 3113. They were asking sum of eigenvalues of the matrix M equal to A square minus 4A inverse. They were asking sum of eigenvalues of this matrix M. Now this is expression in terms of A. Now let us try to find eigenvalues of this matrix at first. Now here what is my matrix A? A equal to 3113. So 3 plus 1 is 4. Sum of column 1 is 4. Sum of column 2 is 4. So one of the eigenvalue of A is 4. But already trace is 6. 4 is covered. So second eigenvalue is 2. Therefore 4 and 2 are eigenvalues of this. But using this, let us try to find eigenvalues of M. So therefore, the first eigenvalue of M is, replace this A by first eigenvalue 4. So this is 4 square minus 4 into 4 inverse. So this is 16 minus 4 into 1 by 4. So this is 15. So one eigenvalue of M is 15. Second eigenvalue of M is, replace A by second eigenvalue 2. So this is 2 square minus 4 into 2 whole inverse. This is 4 minus 4 into 1 by 2. So this implies 4 minus 2, this is 2. So the eigenvalues of M are 15 and 2. Therefore, sum of eigenvalues of M, that is nothing but a trace. Sum of eigenvalues means trace. So trace of M equal to 15 plus 2. This is 17. Just by using spectral theorem. Note this. Now with this, we have finished classroom workbook questions on the concepts Cayley-Hamilton theorem and spectral theorem. Now we move to the concept system of linear equations. System of linear equations. This is the last topic in chapter 1, that is linear algebra. Now let us start this. What do you mean by linear equation? Suppose I have m equations involving n number of variables. Assume that those n variables are, for example, x1, x2, x3 and so on, comma, xn. Now, if the power of each variable in each equation is either 0 or 1, then such equations is nothing but system of linear equations. I have m number of equations, n number of variables Assume that those equations are x1, x2 and so on xn. If the power of or if the degree of each variable in each equation is either 0 or 1, such system is called system of linear equations. Linear means degree can be either 0 or 1. So if in all equations, if the degree of each variable is either 0 or 1, then such system is called system of linear equations. Let us take an example. Suppose I have 2x plus y equal to 9. Suppose x minus y equal to 8. Now in this case, I have two equations in two variables. So in this case, number of equations and number of variables are same. But this may not be true in all possible cases. Sometimes number of equations can be 72. Number of variables may be 71. Sometimes number of equations and number of variables may be same. That depends upon situation. So let us start with simple example. This system contains two equations in two variables. Here we have two variables x and y. The powers are x1, 1. Variables are xy. The powers are 1, 1. So this system is nothing but system of linear equations. Now this equation can be represented in the matrix form like this. Coefficient of x is 2. Coefficient of y is 1. Coefficient of x is 1. Coefficient of y minus 1. Into the variables are x, y. Equal to right side coefficient, right side values are 9, 8. Now this is in the form a into x equal to b. Now this A is nothing but coefficient matrix because this is the matrix obtained by considering coefficients of all variables. Therefore this A is called coefficient matrix. And we define another matrix, that is A slash B. This is not multiplication. First write matrix A and then matrix B. Matrix A is 2, 1, 1 minus 1. Just introduce the column of B at the end of A. This is 9, 8. The size is 2 by 3. And this matrix is called augmented matrix. This matrix is called augmented matrix. So let us try to understand what is coefficient matrix, what is coefficient augmented matrix. Coefficient matrix is the matrix obtained from system of linear equations by considering its coefficients. Augmented matrix is nothing but a matrix obtained by appending column of right side matrix at the end of A. So therefore in the future, probably in the next sessions, we need to discuss the consistency of system of linear equations. When we discuss few equations, my ultimate choice is to find the values of x and y. So sometimes they may have many values of x and y satisfying those equations. So for confirmation, we need to discuss what is rank of A and what is rank of A slash B. So first try to write these points. If the powers of all variables in all equations, if the powers of all variables in each equation is either 0 or 1, then the equations is called system of linear equations. Example, start with this and work out this. I think this point is very clear. So whenever you have system of linear equations, such system is always represented by Ax equal to B. So here we need to discuss about two matrices always. One is coefficient matrix A, another is augmented matrix A slash B. These two are key factors in the analysis of system of linear equations. Now let us start definition of consistency of system of linear equations. That is consistent system of linear equations, or simply we call it as a consistent system. Suppose I have a system of linear equations denoted by Ax equal to B. Now, when I start with this system of linear equations, Ax equal to b, here I do not know how many equations are there, how many variables are there. That is not required for us right now. So, we have m system of linear equations in variables, so which is denoted by Ax equal to b. If this has at least one solution, if it has at least one solution, then this is called a consistent system of linear equations. If it has no solution, then this is called an inconsistent system. Inconsistent system. Let me start with an example. Suppose I have x plus y equal to 8, 2x minus y equal to 7. Now try to get the values of x and y. Add these two equations, plus y minus y. Add these two, you will get 3x equal to 15. So x value equal to 5. Replace x value 5 either in this or in this, you will get y equal to 3. Therefore, these two equations have the solution x equal to 5 and y equal to 3. So these equations have at least one solution. That's why it is called a consistent system. If the system of equations have no solution at all, then that system is called an inconsistent system. Right? Note these points. If Ax equal to b, if Ax equal to b has at least one solution, if Ax equal to b has at least one solution, then it is called a consistent system. If Ax equal to b has at least one solution, then it is called a consistent system. Now work out this example. Note, if Ax equal to b has no solution, if Ax equal to b has no solution, then it is called an inconsistent system. If Ax equal to b has no solution, then it is called an inconsistent system. Now in the future sessions, what we discuss in this concept is consistency of system of linear equations. So what do you mean by consistency? If the system has at least one solution, then it is called a consistent system. At least means it may have more solutions also. More solutions. That means if a single variable takes multiple values, then definitely the system has many solutions. Therefore, in consistency we have two categories: consistence with one solution, consistence with infinitely many solutions. Therefore, when you go through large number of system of equations, for example, I have 30 equations, 42 variables. Is it so simple to analyze its consistency? Certainly not. Therefore, rank is one suitable technique to get the analysis of consistency of system of linear equations. Probably we discuss these points in the next session. So thank you so much.